So this is problem 1.9 in Cook, and it's asking you, basically this is asking you to look at the following beam. This is X, and they want you to basically compare this to a 4-element model like this. Where probably the reasonable thing would be at the midpoint, we get the right cross section. So the actual beam sits like this. Okay? Put the same load on here. And we want to look at the differences in the stresses and the displacements. Okay? So this first beam has a length of L. Well, they both have a length of L. The height here is 4h0, and then the height at this end is h0. The first part of the problem is they want you to find the elongation of the beam, the tapered beam. Okay? So the way you do that is you know the derivative of the displacement with respect to x is the strain field, so we can get the following, epsilon dx, then you integrate both sides, and you get that the displacement is a function of x equal to the integral of the strain dx plus a constant of integration, and the constant of integration is such that the displacement at x equal to L is equal to 0. Right, because that's the fixed point. All right, this is x equals 0 and x equal to L. Okay, so let's do this integral. The total elongation is going to be well, actually, we should probably do the integral backwards. Let's do it from x equal to L to x equal to 0. Okay? So that's the total elongation of the beam. I think that'll give me the right sign. It really doesn't matter, it's just going to flip the sign. I know the displacement, since the compression has to be to the right. I think that should give us the right sign. Okay, so the strain is the stress over Young's modulus, and then the stress is the force over the area, and the area is a function of x. Cross-sectional area changes, and it tells you that this has a thickness here of t, so the area is t, and the expression for the height is, it starts at h0, and then it goes to 4h0 at x equal to L, so we do 3h0 x on L. So if you put x equals 0, you get h0. You put x equal to L, you get 3h0 plus h0, 4h0. So t h0, 1 plus 3x on L. Okay, so that tells me that the strain is P on E t h0 1 over 1 plus 3x. Let's multiply by L so I get the following. And now we want to do the integral on that, right? So we want to integrate. The displacement is the integral from x equal to L to x equals 0. Well, I should put this, the PL on ETH0, and then I get dx over L plus 3x. All right? And the way you always do these integrals is you try to make it look like a net, the 1 over something, So let's do a substitution and let's let y equal L plus 3x. So that means that dy is equal to 3 times dx. And then the limits of integration are going to be such that x equal to L, y is 4L, and at x equal to 0, y is equal to L. So this then becomes the elongation. This is at x equal to L, x equal to 0, excuse me, is P times L on E T H naught, the integral from y equal to, putting an L into here, 4L to y equal L of dx is 1/3 dy, so I can put a 3 down here, dy over, and now this just becomes y. And so this indefinite integral is just the log of y. So we have the displacement at L is equal to, I'm sorry, at 0 is equal to PL 3 ET H naught times the log of L minus the log of 4L. And so this is the same as dividing, so that just becomes PL on 3 ET H naught log of L over log of 4L, so that's just the log of 1/4. Okay? So that's the displacement. It's positive and it's just going to the right. All right? All right, that's part A. Now, part B wants you to compare the displacement using 1, 2, and 4 elements. Okay. So if we were to do the 1 element case, well, maybe I'll pause here. Why don't I pause here? Because this might get a little long. And then we can do the part B.